Okay. I'm happy to welcome Brendan, who's going to be talking about Duckietown.
Thanks, Ryan. I'm Brendan. Buenos dias, Madrid. This talk is in English. I'm from the University of Montreal, and as Ryan mentioned, I'll be talking a little bit about Duckietown. Duckietown is a low-cost platform for autonomy education and research. Started at MIT a few years ago, and since then it's grown to a bunch of universities around the world, hundreds of students involved. And it's a great way to get people introduced to some of the concepts in robotics, from perception to planning to control. And through these, they can develop some cool applications. So it's a kind of a hands-on classroom with miniature autonomous vehicles. This is one of the instantiations of Duckietown. They can grow to be quite large. The specification is that you have a standard Duckybot like this and a lane that's marked by tape. It's all pretty cheap, but it has some good hardware to capture about 60% of the problems you might encounter in a real large-sized car. It's got a camera and 2 actuating wheels. These are some of the localization towers that they have. So the overhead cameras, we call them watchtowers. And we have these April tags, our fiducial markers. So Duckietown is, you can build your own at home, or there's a bunch of these in universities. And they have a bunch of traffic cameras for us to get a traffic view of the Duckybots. And the Duckybot itself, which is here navigating an intersection. So the latest version of the Duckybot is a Raspberry Pi 3B Plus with a custom hat, and has a camera, and as we mentioned, 2 wheels. These are not differential drive because they're simpler to operate. And last but not least, the Ducky is part of the spec. So we have a passenger. Very important. So the lab that I'm part of is interested in deep learning and applying this to some of the components in the robotics stack. Here we only have a camera and wheels, so we're thinking, well, what are some of the applications of this in robotics? And in general, the kind of classic pipeline is kind of hand-engineered and hand-tuned. But we'd like to explore how some of these components can be replaced, or at least compare them to state-of-the-art methods in the robotics community. So this is kind of sets the stage for what we're trying to do with Duckietown at home and abroad. So there's 2 Duckietowns. There's a virtual Duckietown and a physical one. The physical one is a test bench for exploring some cool applications. When you deploy this to the Duckybot, it's really cool to see it in action. But it turns out that it's kind of difficult to collect the data you need to feed some of these algorithms. So these architectures require a lot of data in order to generalize well to new environments. And it turns out what you really care about is not necessarily the Duckietown itself, working in that, but the generalization behavior, so how it handles new situations. And so if you were to do this in the real Duckietown, you might have to collect lots of different trial runs with the lights on and lower and different temperature settings. And this is not so ideal. So we'd like to be able to collect lots and lots of data. And this also helps us simplify the reproducibility of these experiments. So if we can set up all the initial conditions just like we saw them before in another run, then we can test this later on for different conditions. So we can set up scenarios and do integration tests. And the nice thing about this is you can augment it with lots of different types of data that you might not encounter. So one of these simulators we developed is the one I'm about to show you now. This was developed in-house. It's a pure Python OpenGL simulator. We explored using Gazebo for a little bit, but it turned out to be a little bit slow for the inner loop of the machine learning. So we ended up developing our own. And this is imitation learning example. So a human's kind of driven it around, trained this, and this is a pre-trained model running in the simulated Duckietown. So the field of machine learning is kind of evolving. It's changing over time, and that's both in terms of the high-level kind of abstractions you use to write these architectures, as well as the hardware and the drivers and the middleware in between. And this is a cause for some variability in your applications. So we'd like to try to minimize that and make it easy for researchers and students to easily reproduce and repeat prior work. So that kind of motivates some of the work that we were doing in reproducibility. So with these new hardware platforms, we'd like to be able to easily port some existing architecture onto that without reinventing the wheel. So there's a lot of work in machine learning going on right now in reinforcement learning in developing these simulator environments. So OpenAI Gym is one such platform that allows you to, it's an API where you can kind of do the reinforcement learning paradigm. That is, you send out an action and get a state and reward back from the environment. But machine learning kind of has this endemic problem of bias and variance, and it's a little tricky sometimes to tune these parameters to get the best or the safest behavior and operation that you'd like. So this issue kind of plagues a lot of models when you train them. And so this is something we'd like to be able to rigorously test to see whether these are behaving like we want them to. Overfitting is another issue that kind of is very closely related, that causes some models to pick up on features in the environment that they're not supposed to. So in order to prevent that, we use a technique called domain randomization, which takes some baseline environment and adds textures and kind of features in the background to sort of throw off some of these biases. And this turns out to make it more robust in generalization, so it'll be able to characterize the features that really matter rather than these kind of spurious things that it might latch onto in the background. And this technique is pretty powerful for getting it to work well, both for reinforcement learning and kind of standard supervised learning. This is one tool in the toolbox that they often use. So the software is changing as well. I'm not going to go really into depth about this, but this is a really interesting blog post by Andrej Karpathy. It talks about the evolution of software over time and how we're moving towards these kind of differentiable architectures. They have a lot of benefits in that they're kind of agnostic of the hardware that they run on. They're just kind of matrix multiplies and things like this. They port very well. But there are some limitations in that they're not very interpretable, and they have these failure modes that can be difficult to intuit why these things are going wrong. They're subject to kind of a lot of adversarial attacks. And these are kind of difficult to prevent, but we'd like to be able to test for various failure modes that we'd like to avoid. And so this is one kind of setback of this new software the evolution of the software itself. And finally, robotics is kind of, people are exploring, well, how can parts of this pipeline be replaced? And I'm not going to claim that machine learning will take over this entire stack, but we're interested in exploring how certain pieces of these components, such as perception, can be replaced with a learned architecture. Yeah, so this is kind of tricky. You want to be able to compare against a baseline, and in order to do that, you need to have some kind of modularity in your architecture. So I don't want to go into a whole lot of depth here, but in the idealized kind of story you hear in the textbook, there's an agent in the environment, but it turns out in reality that the boundary between the agent and environment is much more fuzzy than you'd like. Depending on where you draw the line, your simulator will have to take care of these, generating the correct optics or the modeling the dynamics of the hardware you're running on. So what would you consider to be the agent and what you consider to be the environments is kind of an important distinction. Okay, so just talk a little bit about work we've done on Duckietown. Originally, Duckietown had a pretty difficult installation and setup procedure, both for the students and for the Duckietown administrators themselves. They are running kind of a graphical stack with a bunch of shell tools. You have to install some libraries. And the installation instructions, were a couple chapters, I think. So we're trying to simplify this. So we wrote a little wrapper around it to set up, to flash the SD card and to use this containerization tool called Docker. It has some benefits, which I'll talk briefly about. But you can go one way or the other. And it turns out there's a balance to be struck between automating too many things and making sure that people understand what's going on underneath the hood. So this is also a tool for teaching, so you want people to understand what's going on. So something to keep in mind. You can over-automate. But today, all they need to do to install a DuckyBot with all the applications pre-installed is flash the SD card, plug it in, boot it up, and then run an app. These are some of the nodes we were running. And you want to try to modularize these or make them into their own Docker containers. And so, from the camera node to something that corrects for illumination all the way to the controller, you want to have these be reproducible, binary reproducible artifacts. So the idea is that very often when you're building these things, if you don't pin a version or you don't very carefully specify the things you need to build these, then they can drift over time, and you end up with incompatible versions and so forth. So Docker offers some nice benefits for us. Primarily, the reproducibility benefits are what we're interested in, but they also offer these isolated kind of sandbox environments. So we can gracefully kind of degrade the quality of service and examine how that affects each of these different components. We can kind of give them hard limits on resource utilization and so forth. So there's service discovery. There's a whole bunch of features. The Docker ecosystem is pretty large and well developed. But we were kind of concerned initially, well, this is going to port well to these mobile devices, these Raspberry Pis. Is the overhead going to be something we have to worry about? And it turns out you don't really have to worry about that, which is nice. Some disadvantages are there's learning curve, and if you're trying to set up graphical user environments, this may be a little bit more tricky. And there's an initial kind of investment in migrating your code to Docker. But we're convinced that the benefits outweigh the disadvantages. We have a kind of web management UI for people who aren't so comfortable using the command line. This allows you to start up and run demos and applications, download some Docker images, and manage your Docker daemon from inside the web. So that gives us kind of a nice way to avoid SSHing into the DuckyBot and transferring files and so forth. There's a few different deployment models we explored. One was directly from the laptop to the DuckyBot. One is pushing up to a cloud provider like GitHub, having it build on Docker Hub, and then pulling periodically from the DuckyBot. All of these are possible. And how you do this kind of will motivate some of the other architecture choices you make. But automating this is really important if you want to be able to use best practices in software engineering. So we ended up with a classic kind of ROS stack was Raspberry Pi with a thin hypervisor or operating system that just takes care of the Docker setup and the initial boot. And then we put Docker on top of that, which comes with Docker. We don't have to do anything. And we install some of our own Docker layers there. And finally, on top, we have our demos and ROS nodes and so forth. So the nice thing is there's this tool called QEMU, or QEMU, that allows you to run the same binary artifact on an x86 machine and then run this on Windows, Mac, or whatever you so please with an X client if you need a GUI. And then so that allows us to do our tests on the x86 machines during the auto build. And so that's something we figured was pretty useful to have. So these are the two stacks side by side, kind of joined by the Docker layer there that allows you to kind of port them one from one to the other quite nicely. So this is what we ended up using, something like this with an emulator layer on the x86. A few lessons we learned in the process. You have to be careful with Docker, doing crazy things with Docker. So you don't want to set up like a Rube Goldberg machine with all of these layers. It turns out that when you rebuild one, and these changes can propagate and cascade through a bunch of different containers, and you kind of have to be careful of how you tag them and manage the versions. So it's important to have a versioning scheme from the outset so that you're pinning each of the versions of these things instead of just publishing to a latest build like we originally did. And then don't try to over-automate like we said earlier. Try to compile and run tests during the build so that if something doesn't work, it will fail the build and you won't publish the image. This is a nice thing to do. We found that if you're compiling all these libraries, you don't really need to. There's a ton of people who do pre-compiled libraries for ARM. PyWheels is a great resource, so utilizing that pretty heavily. And then, if you're doing that, just be considerate of how long this takes to build, because someone or some change can kind of really slow down your development process over time. Docker has a nice feature for caching, so if possible, try to use that in your CI/CD tool. Docker Cloud provides this as well. So this is some of the infrastructure we're using to host the AI Driving Olympics, a new challenge for NIPS and coming up in ICRA 2019. The three primary challenges are lane following with obstacles, as we saw, fleet management, kind of mobility on demand, kind of coordination stuff. And so you can register for that today and start getting up and running on this infrastructure. And we use a GPU to run the simulator and do some machine learning for that. I don't have a whole lot of time to go into this, but there's a nice migration, a gradual migration procedure for that. So just to recap, there's kind of two groups of users that motivated our architecture. One was the researchers and the students, and they both want this nice user-friendly tooling. So this is one thing that we really wanted to do, and it served both of them pretty well. We were able to kind of really simplify the deployment, the build and deployment model, get a handle on some of these dependencies and really specifying them very carefully. And some future work we'd like to do is hardware in the loop, so set up like a test bench for the Raspberry Pi connected to the simulator so we can kind of gradually deploy this from stage to stage and then fail it early. As a kind of a plug for a side project, we have this tool called Hatchery, and It does some static analysis, navigation, code completion, and helps you deploy your code to the DuckyBot. If you're interested in this, we're interested in hearing your feedback, and if you're interested in a tool like this, we're welcome contributors as well. You can hear more about this on the GitHub. And I'll finish with a special thanks to my mentor, ros-i Christov at Newtonomy, and my advisor, Liam Paul at the University of Montreal. And I'll leave you with a video of this running in the real world while we take questions. This is sim to real, so it trained in the simulator, and it's running autonomously in the DuckyTown.
Thank you, Brendan. Have any questions?
Yeah, so I think I have to ask the question that's on everybody's mind, which is, what is the anti-Instagram node?
So this is corrects for. Sorry, the question was anti-Instagram. Nothing to do with the social media platform. It corrects for illumination variance. Does a k-means clustering of the colors. So there's white, yellow, and red, and the lighting can vary from place to place. So this is kind of a hand-designed correction mechanism for that.
And what's the best place that people can go to find out more information, get involved, try things out?
Duckietown.org. There's a page for the AI Driving Olympics, as well as a guide for instructors and students, kind of do-it-yourself learners and things like that. All that's, the docs are open source, as well as the code on GitHub. You'll find links to that on duckietown.org.
Great, thank you.
Thanks, Ryan.